with that, we will move to our third and last pre-recorded speaker. And this is from Dr. Jason Hattrick Simper. So Jay he's a researcher at NIST Gaithersburg, so National Institute of Standards and Technology. And his talk is, where exactly does one actually use AI in material science? So if we could go ahead and start Jay's talk, please.
All right. Well, thank you for attending this webinar. My presentation today is going to focus on where exactly does one actually use AI in material science from the perspective of an experimentalist, somebody who wants to use these techniques to make my job easier or facilitate more rapid knowledge extraction. So if we think about the scientific method today, what do? We collect and feed archival data and knowledge. We take these, we gather them up together in our graduate students in our own brains. We create some sort of predictive model in our brains. From that, we then recommend materials or experiments to do. We make the materials. We characterize them. We take whatever amount of data that we have, big data, small data, intermediate data. We clean it, we process it. We then take it into something where we're extracting knowledge from it and getting actual information, which we can then feed back into our archival data, our brains, create a new predictive model, and so the pattern continues. So when I think about AI in material science, the first question I ask is, where are we using it? And so if we think about material science, and we sort of cut it down through 4 pillars, we have hypothesis generation, new data acquisition, data processing, and knowledge extraction. Are we touching each of these pillars inside of the material science community? And if we are, what's to prevent us from taking our hands off of the wheel and letting the car drive itself? So let's talk about hypothesis generation. Most techniques that you use in AI require some initial data to seed model generation. It's important to identify where is this data coming from, because it will tell us a lot about the biases contained therein. We have to keep in mind that we're not just churning compositions and properties through a mystery machine. All models need effective descriptors. They can be chemical, they can be structural, they can be both. But we need descriptors to give the machine something that it can read and build a model off of. There's debate. Do ML models explicitly contain physics or not? Sometimes yes, sometimes no. And how are the physics encoded as hard or soft constraints? And then finally, there's this idea of extrapolative versus interpolative. And we're going to come back to this a lot of times during the webinar, because we have to identify what's the best balance between those for materials optimization, for instance. All right, so an example, and I'm going to go through a series of examples, and I'm going to try to highlight where they got the data, what are their descriptors, and what algorithm are they using, and then what do we get from it? So this is an example from Chris Wolverton and Logan Ward, where they basically chewed up Landau-Bornstein. They said, okay, let's look through all of the alloys that make a glass or not, and let's pull out all 6,000 of them, and let's give them composition-based chemical representation. So they contain things we know: covalent radius, radius of ions, electron affinity, density, melting temperature, and then it basically uses weighting to combine them to account for alloying. You can then build a relatively simple machine learning algorithm, in this case, random forest, which can tell you whether or not an alloy will form a glass or not. And now we can turn this loose on the entire periodic table, or the subset that we're interested in. And all of a sudden, we've got 24 million alloys that we could potentially make in ternary and quaternary space, of which about 75,000 of them are potentially metallic glasses. And so we've constrained a very large search space, not using eutectics or atomic size explicitly, but using a model that basically is doing a classification pass-fail. Alternatively, we know that chemical information isn't sufficient. We know that structure is important in determining the properties of material. And so this is an example from Kamal Chaudhry, where they basically use pair distribution function to be a proxy for structure and use that in addition to the chemical descriptors as an overall chemostructural descriptor. Moreover, making a prediction of a material composition with a property isn't sufficient if the material is not stable. And so they use genetic algorithms once they've made a prediction to predict whether or not that material sits on or close to the convex hull. And this is an example of pulling information from online databases like AFlowlib, Materials Project, OQMD, and of course their own proprietary data set. From this, you can even begin to visualize what the space looks like. And at the end of the day, you can even go to their webpage and plug in a CIF file and get a prediction of properties if they have sufficient data. But we don't always need such a broad set of chemical or structural descriptors. Sometimes we have a really good idea of what causes a material property. So in the case of looking, for instance, at ferroelectrics, we can isolate our material's features down to a handful, electronegativity, volume, right? And now we can start to talk about building regression models that will describe how those properties change as a function of composition. From that, you can create millions of potential possible compounds. And then you can play this trade-off game. Exploitation. Do I go after the highest value and just keep going up the hill? Or do I attack something like the uncertainty that's naturally built in to, for instance, on the right here, your Bayesian inference, where you basically build a function with known error. And now we're attacking, instead of exploitation, we're attacking our uncertainty so that the model becomes overall more predictive. And so here again, this is the Bayesian process, the Bayesian plot that many people see. And so you can either attack going up this slope to the maximum possible value, although your uncertainties blow up, or you can attack the uncertainty. And what Turab found, actually, Lookman found, was that if you trade off between them, doing exploitation for a while and then exploration, you more rapidly converge on optimal values of the strain, and overall your model does better than either exploration, exploitation, or just random search. Another potential resource for gathering data is your own instrumentation. This is an example from the National Renewable Energy Lab. They have this very sophisticated LIMS system where basically you have a nebula of instruments all hooked up onto this automatic harvesting server that once a day or twice a day comes in and grabs the data from your instrument, converts it into something that's machine readable, throws it into an experimental database that sits on campus, which you can then use an API to access and visualize the data, see what they've done, see what material systems are interesting, but also run analysis and visualization to try to understand the underlying material science associated with this. But materials predictions are not useful if we can't make them. And worse, if I can make it and no one else can, my work really isn't that impactful. And so when it comes to using AI to predict whether or not a material can be synthesized, I have two options. I can learn from the literature what's worked before, or I can create a framework and make sure that it exists so that we can have transferal of material synthesis protocols. So here's an example from Josh Schreier from Haverford College. Brilliant idea. There, in our students' lab notebooks, there are thousands, hundreds of thousands of failed reactions that never get published, never see the literature, but contain valuable information in machine learning, bias in the data set, particularly positive bias, destroys your ability to make a predictive model. And so what Josh's team did is they went through a bunch of graduate student notebooks, recorded the reactions, used the normal descriptors, reaction and reactant chemical descriptors, created a large database of reactions, and then used a support vector machine to create a model which could then make recommendations for new materials to synthesize and how to synthesize them. A problem in ML, though, is interpretability. As a human, I can't look at a support vector machine and get much physical intuition out of it. So instead, what Josh and his team did was they built a model of a model They built an interpretable decision tree, which a human can read and go down and identify how to make something, why did it work, and build hypotheses that they can then test in their reaction database and predict new materials and new synthesis routes. Another way of skinning this cat is to go through the material synthesis articles. So look through all of the known literature. This works really well for hydrothermal or physical grinding. Use natural language processing to look at the experimental methods section, identify what was made, what did we use, what amounts, what were the techniques applied, and then compile these synthesis parameters and create a planning resource whereby, for instance, if I were interested in growing titania, I could say, well, if I was going to do it hydrothermally, most people seem to anneal it below 200 C. If I'm going to calcine it, I'm looking at somewhere around 500 C with some excursions to higher temperature. And so now at least I have an idea of how people have done this before, where are the unexplored places, but also what's been successful in the past. And this allows me to make a cost-benefit analysis about whether I want to explore new synthesis techniques or exploit what's already available. We have the samples. We can characterize them. Data processing, cleaning, and feature identification now becomes the bottleneck. As we all know, raw data are noisy, they're filled with artifacts, and per pixel, they have very little information. In the field, people are using AI methods to denoise data, to remove spurious artifacts, to perform preliminary analysis, and also, in some cases, to identify features, just at a high level, not at the point of knowledge extraction, but just to give you an idea of kind of what are the trends on your wafer. Example of unsupervised denoising comes from Oak Ridge National Labs, Alex Belyanov, and what he has done is said, okay, in my STM images, my STEM and my STM images, I have regular atomic arrays. I can use the periodicity of that and cut my 2D image into a series of pixels of size M by M, splice my data out, and then reconvert it into this vector analysis, this vector form, and use something pretty simple, principal components analysis. What principal components analysis is going to do is it's going to orthogonalize the data and cut through variance. And at the end of the day, the things with the most variance are the most informative. The things with the least variance often contain, they're information poor, they're less correlated, and oftentimes are associated with noise. And so, for instance, for a STEM image, you can see in the original image, you have a lot of noise, but you can sort of see the positions of the atoms. You then window it out, do your PCA, do a cutoff is somewhat arbitrary. This is unsupervised, and so the user has to come in at the end and decide what's noise and what's not. But if done properly, at the end, you come out with a nice cleaned image showing the atomic positions very carefully, and also the removed noise, which you can then use in other contexts. Data processing, particularly data on stream, is a huge issue, particularly for our folks that are doing things like synchrotron experiments that are very expensive. And so if you look, you have data that's very high quality, you've got data that's noisier, and you want to be able to parse those between. You want to say, okay, maybe we need to count a little bit longer on that sample. There are things that happen during synchrotron experiments, like the beam was blocked by sample holder, and so you miss out on all the data here. And you also want to optimize your coverage density. You want to make sure that you're getting the maximum amount of information out of your dense scan. And so what we have been working with the Meta at Slack for years doing is taking our raw diffraction, creating a workflow in real time that takes our raw images, transforms them into diffraction space, does some reduction, some background subtraction, some peak identification, and then spits us out information that we can use while we're taking our experiment to identify what's our signal to noise, how many peaks do we have, how crystalline are our samples, with the eventual idea of going into this autonomous feedback loop. The next big issue is knowledge extraction. For HTE groups, this has been the single most important step for the past 15 years. If I have 30,000, 40,000 diffraction patterns across 14 ternaries and different annealing temperatures, how do I pull information from those? How does one simplify multidimensional data either via visualization or outright information extraction? How can AI be used to optimize experimental measurement time, particularly for things that are expensive to measure? And how can AI make redundant tasks easier so humans can focus on high-level tasks, the things we're good at, things that we'll always be better at than AI, hopefully. So one example of this, for instance, would be looking at piezo force microscopy using IV acquisition with Bayesian inference. And so the idea here is that you want to measure the polarization of your sample as a function of voltage, but you have a real property, which is this resistance of your material, and a property that varies as a function of time. So as I apply the voltage, I have to wait for it to calm down so the capacitance term disappears. What the Oak Ridge group was able to show is that they can actually take their measurements live on stream at 4 kilohertz, use Bayesian inference and a working model of their material, and actually extract out the material-specific polarization curves with uncertainty. And so what that enables you to do is look at materials 500 times faster than you would ordinarily be able to, and pull out things like positionally sensitive polarization information, or pull out the lossiness if you take that information and then do k-means clustering on top of it. And so this is a multifold acceleration of materials discovery and understanding, and allows you to get to the science quicker. Another option is to do something like deep learning, which is very of the moment. This is an example from DeCoste and Home from Carnegie Mellon. And so the idea is you use a convolutional neural network, and you use a series of layers where the first 2 layers seem to do a very good job of picking out edges. The next couple of layers are starting to pick out precipitates and other small materials things. You can then upsample and create on an output a classifier that says, this is your iron carbide, this is your depleted zone, denuded zone, this is your matrix material. And then on top of that, now you can start to ask interesting questions of hundreds and thousands of images that were taken and analyze automatically. You can say, well, what's the impact of temperature here as a function of temperature, represented function of color, represented in a t-SNE plot, and annealing time here, basically the size of these blobs, on what my final microstructure, which is represented here on the left of this image. Moreover, this allows you to free up your graduate students, your postdocs, your technicians to spend more time thinking about science. So pulling out the width and the distribution of the denuded zone for this steel is a time-consuming and laborious task requiring a lot of pixel-to-scale analysis, whereas a convolutional neural network properly trained can pull this out in seconds, do this for hundreds of images, and then give the scientists something, information, knowledge that they can then use to build a model that helps them to understand their world. There are a couple of different ways that we've done this over the past couple of years. One of those is to use supervised knowledge extraction. The idea being here that humans look at these patterns, pick out particular features and say, that one's alumina oxide, that's nickel oxide, that's gamma alumina oxide. And then from that, they can build up this composition versus time or temperature phase map that tells us about the stability of the material. A computer can do that just the same, but with a more limited, but it needs a training data set. And so in this particular instance, you have to pull out representative data, and you can use unsupervised techniques to do so. Have your students label that subset of data, maybe 1/10 of the data, 15% of the data, and then use things like, is the slope up or down? Is that a peak or not? And actually classify out and pull information from the pattern, which it can then use to train a classifier, and then turn it loose on the rest of the data and get the same plot out. Conversely, since this is human intensive on the front end, the other way of doing this is in an unsupervised manner, which is generally human intensive on the back end. So an example of this is non-negative matrix factorization. And when we think about diffraction patterns of multi-phase materials, one of the ways that we can think of them is as linear superpositions of A and B weighted by the proportion that they're there, and also some X-ray scattering efficiencies plus error. Using that type of a framework, you can basically pull out these basis diffraction patterns automatically. And so that one's likely noise, that might be BCC iron. Your students can then go in afterwards and label each of the peaks. This is peak shifted BCC iron, most likely. But the point is, on the back end of this, you get a phase diagram that has not only the different phase regions mapped, but also the proportions of each of the phases that are present inside of each composition. If we can do this, and it's all automated anyway, why don't we do this on the fly? Why aren't we doing our analysis as we're taking our diffraction patterns, not just getting some information about noise and number of peaks, but actually mapping the phase diagram? This is a report from Kuzney et al. From 2014, looking at this ternary system where they were actually in control of the synchrotron system, sending data back and forth between California and Maryland, and performing on stream the analysis of which phases are present where in the composition region. So I think I've illustrated to this point that basically machine learning has been implemented in ML and AI throughout the material science 4 pillars. And the idea now is, can we close the loop? Can we do something like what was suggested in this wonderful report called the Materials Acceleration Platform, which is put the AI in control using modular robotics, a good data infrastructure, and inverse design to create this autonomous discovery loop and create autonomous materials research systems. It's not just this report. People are starting to catch on to this. This is from Jim Warren, who's a TPD for materials genomics at NIST. And he says in the next 5 years, AI-driven autonomous materials research is going to fundamentally change how we do material science. So for instance, in the case of Benji, he's growing carbon nanotubes using a Robbins system. He basically has an AI in control that's training and telling the thing what laser power, what temperature, what gas flow to use next. And then from that, he's able to tune the growth rate of carbon nanotubes from something that's very noisy and highly non-optimized through 600 experiments to something that's increased the kinetics by 3 orders of magnitude over the worst performing value. All by itself, without human intervention other than to change the gases. That is amazing. Another opportunity or another example of this is ADA, an autonomous discovery accelerator with Alon, Jason Hine, and Curtis Bellinger. And so in this particular case, this is an example of trying to use imaging and chemistry knowledge to match a color. In this case, they're targeting this particular color. So the robot mixes chemicals, puts them down, takes an image, computes the RGB value, and determines how close or how far it is. What you can see is that most of the values are high up here, and then every now and then something drifts down. That's not error. That's actually the machine actively saying, okay, so for this step, let's try to mess it up. Let's try to see if we go far off of the minima if we're going to be able to find something new and interesting. And so this is a machine that matches colors using chemistry, chemical knowledge, and machine learning by itself. And this is just the start of what they're doing there. We also have work by Gilad where fundamentally we're mapping phase diagrams, trying to identify the boundaries between phase regions using baseline knowledge from something like ICSD or AFlowLib. And so what you have here is a map of the phase diagram. Here's where the boundaries it thinks it are. Here's how uncertain it is about whether or not those boundaries are there. And here's the machine saying, I want to measure that point next. And then iterating through, moving the boundaries, taking the next measurement, and fundamentally, with an order of magnitude reduction in the number of experiments, arriving at the correct answer, which is displayed on the top left. The next step is what happens as a function of temperature and time. We know that materials change by both of these processes, and we'd want to be able to map these phase diagrams as accurately as possible. What Brian DeCoste has been doing over the past year or so is training a Gaussian process classifier to take diffraction measurements as a function of composition and temperature, and to accurately map out the composition ranges using uncertainty in terms of the classifier. And so if you look at this scan, if I were to dense scan this vanadium tungsten film, I'd be talking about doing 2-3 days easily, constant X-ray diffraction measurement. As it stands right now, we're able to create these types of phase maps in less than 12 hours. And what it does is at each temperature increment, it basically says these are the phase regions I think I see, and these are the 2 next most informative spots that I would like for you to measure so that I can minimize my uncertainty moving forward. So just to conclude, it's our opinion, my opinion, AI and ML are already prevalent in materials throughout the 4 pillars that I described. They're not panacea. They're going to replace human intuition and creativity. They're merely enablers. In some select cases, you can see multi-order of magnitude increase in the acceleration of materials exploration and discovery. It might be fairer to say that AI's true influence is going to be on the rate of hypothesis generation and validation or invalidation, how quickly we can ask questions and get to answers that make sense. AI needs fair data, including negative results, to be effective. It's not sufficient to plumb the technical literature because we're very positive biased there. You have to be able to balance your data set with negative results. I would say full materials research autonomy for very specific problems has already been demonstrated and is being applied. And this is going to accelerate in the next couple of years. I'd like to point out that we have a boot camp on materials research, machine learning for materials research every year in collaboration with Stanford, ORNL, University of Maryland. And I'm the idiot. This is my village. Thank you.
Thanks, Jay. That was a great talk. I think it was a tour de force in showing how AI and machine learning can be applied to experimentation with lots of good examples. So let me start then, and I appreciate everyone holding on with us. I think we've had a great webinar, and what I'd like to do is to go straight to a question from AKM sorry, I'm going to get the name wrong, but Shastagir Chowdhury, who asks, if the numerical data are not verified with experimental data, AI can generate wrong info. Any scope on this? So Jay, I'll give you first crack at that one.
Sure. I think that's a great question, and absolutely it's something that we consider every day. This is sort of where this idea of active learning or iterative learning, where the AI model spouts out something, and then you have to validate it either via computation or experiment and then churn on. I think it's actually a little bit more exciting than that in some ways, because the AI often doesn't have our inhibitions. It's not afraid to fail. It's more like a 5-year-old child. It's very curious. And so I have found, at least in my own work, the most interesting thing is to go where the AI says I should go, and I don't think that makes any sense. Particularly, we've been looking at metallic glasses. And then if the model's wrong, that's fine. You retrain it and make the next set of predictions. And the benefit of AI is that they don't forget the failures. They don't bias their own results.
Wonderful. Okay, thanks, Jay. Anyone else want to comment on that? So then our next question is then from Dylan Madasetti, who asks, how do we use machine learning to combine length scales of our understood physics? So that's an interesting one where I think we're always challenged in materials with the, sort of the issues associated with length scales. And so, Jay, I don't know if you had a comment on that.
It's not my particular field, but I've seen a number of people who have tried to use ML to create descriptors that sort of link something like DFT to MD or from MD to something on sort of the continuum scale. The particular algorithms they use, I'm not so certain of, but I'll try to follow up with an email to that individual.
Okay, great, thanks. Chris, any comments on that one?
Yeah, I mean, I think it's a really important question. This idea of not necessarily machine learning or AI, but just multi-scale analysis. And I think where AI or machine learning models could come in are things like hierarchical models, multi-fidelity models, where you are trying to combine information at different scales. And as long as you are honest about your uncertainties and your correlations between the predictions, those could provide fairly accurate, or not accurate, or powerful models in regression or whatever it is you're trying to do.
Okay, great, thank you. So we have a question from Mei-Chen Liu, who asks, have you integrated molecular dynamics into your machine learning processes? If so, any examples?
So I'm familiar with people who do, for instance, molecular dynamics, who have begun incorporating machine learning. Debbie Aldis here at NIST is one of the people in the soft materials field that sort of has been focusing on that for the past couple of years. What I think that you're getting at is when you build these sort of autonomous systems where your AI creates the hypothesis and then has to recommend forward, do I do an experiment or do I do computation, which is the most expedient route and least uncertain to get me an answer. That is something people are really starting to think about. How do I create these autonomous systems that not only control experiments, but might diverge and run computation? And I think Carla spoke to that with her Sarah.
Sure.
Okay, great. So then there's a question from Amit Ranjan. Is it possible to use an experimental phase diagram of, say, a multi-component system as a visual input and come up with a free energy function that might predict the observed phase diagram? Any work in this direction?
So I've seen some interesting work. I saw a talk a couple of weeks ago from Buffalo where they sort of started on this first part of the endeavor. Krishna Rajan was looking at phase diagrams using images of, in this case, two-component system phase diagrams to extract information, to build a model to predict whether or not something could form a metallic glass. Not super familiar with people who are just using the images. Most of the people that are starting to get to asking what we call computational phase diagrams or CalFAD type questions are typically actually just using ML to make recommendations into CalFAD with uncertainties. But I don't see in principle why it couldn't be done.
Yeah, I mean, I'm not familiar with the work, but I've heard stories of people actually using images, and they're pushing it through deep learners that are trained for image analysis, so these convolutional neural networks and things like that, and they are extracting information from that. I think it's really fascinating.
Great. Okay. So I'm going to ask one last very open-ended question before as we wrap up here. And I'll ask Chris to respond and then Jay.
Sure.
And so really pretty simply, just to wrap up a very nice webinar, where do you see the future of this area of AI and machine learning for materials development and design? What's your sort of prediction for the next, say, 5 to 10 years? Chris?
I think, so I'm going to agree with Carla on this one. I think we are in a unique position that our data, it's not like ad-click data or people's behavior on the internet, where a lot of machine learning algorithms are sort of built. That's the context in which a lot of machine learning algorithms are built. Our data is has a fundamental language to it, and that's physics. And so I am really excited about the prospect of incorporating physics in the types of machine learning and AI that we do, both using what we already know and also extending our physics-based knowledge. And how we do that, I think we're gonna need a tour de force of all the different techniques that, for example, Jay was talking about. We're gonna need knowledge extraction. We're gonna need regression modeling and all of that to do that. And I think it's going to be really exciting when we do that. I mean, who knows what the first physical law of computer discovery, what's that going to be, and when that's going to happen. That's going to be awesome.
Great, thanks, Chris. Jay.
Okay, I want to echo the last thing that Chris said. It's, when's the first Nobel Prize in chemistry going to be won by an AI? I don't think 5 to 10 years. I think that that's a little ambitious, but I think that certainly in the next 5 to 10 years, ML and its application in the way that we plan experiments all the way through to final knowledge extraction, it's going to become commonplace. It's going to become something that our students and our postdocs are conversant in, and they're going to be adept at it. I think that in the next 10 years, we're going to move from these sort of boutique autonomous examples to actually implementing these types of technologies, these ideas into workflow, at places like GE, where they're actually churning out turbines, or things like in additive manufacturing, where there's already interest. I think that these autonomous systems are going to become increasingly more prevalent. So 5 years, everyone's going to be doing at least a portion of ML, just because you can't not. What I really hope to see is a increase in the number of data sets available for via this findable, accessible, interoperable, and recoverable principles, so that researchers who maybe work at a university that's underfunded have an opportunity to do real science, just the way that astrophysicists do right now with these large databases from the telescopes. I think that would be a really exciting development to democratize science.
Wonderful. Thanks, Jay. And so, Carla, if you would give your comment on the future of this area.
Well, I fully agree with Chris and Jason. I think, these are very exciting times for AI, but we have a lot to do. And but frankly, I think it is very promising. And indeed, the vision is really how to, develop AI systems that are just like scientists. And AI, we have made tremendous progress, and AI has really advanced in terms of what we call, perception areas. So now we can, AI can recognize objects and has supervision, superhuman skills in natural language, even in Google Translate and face recognition, etc. But, the next frontier is when it comes to incorporating, knowledge, interpretability, etc. But I think material science is a promising example, and to some extent, we can, start by identifying, small topics, and I believe that we can have, autonomous scientists within a few years. There's a lot to do, and we have to go beyond, the straightforward machine learning techniques. We have to, again, as highlighted by Chris and Jason, we have to incorporate the entire cycle of the scientific method. But I have to say, very exciting times for AI, and in particular for applying AI to the next stage of autonomy in material science.
Wonderful. Yeah, thank you for your comments there, Carla. And I would just tag on to that, the idea of having autonomous researchers is, I think, very compelling. And just emphasize, I think what Jay was mentioning, that we, this partnership between human researchers and robot researchers, I think, is what's very powerful, right? So robot researchers on their own will have a certain contribution, but teams of human and robot researchers, I think, will be even more powerful. And to that end, really, if we all have access to our AI researchers, this also, again, really democratizes research to the point where we can expect, perhaps in the far-term future, a return of citizen science. So with that, what I'd like to do is to thank our speakers once again. So that was Professor Chris Reyes, Professor Carla Gomez, and Dr. Jay Hattrick-Simpers. So I would like to thank the three of you for the wonderful presentations and discussion that you gave, and also would like to certainly thank all of the MRS members who joined in on the chat and contributed a wonderful set of questions. So with that, thanks once again, and I will now turn it back over to Bob Brockler from MRS to wrap things up, and again, signing off. Thanks very much.
Thanks so much, Benji, and I will echo your thanks to our speakers, Chris Reyes, Carla Gomes, and Jason Hattrick-Simpers, as well as yourself, Dr. Benji Maruyama, all of whom donated your time to be with us here today, to develop those talks, to record them, and then to spend the full, what ended up being 2 hours with us on the live production. So it's not an insignificant amount of time that each of you donated to this event, and we certainly are appreciative. And of course, thank you to all of our attendees. A lot of you hung in there for the full 2 hours, which is, I think, really indicates the depth of interest in this topic.